This is a review of and practice in Euler differential equations. So this is maybe our first example where the coefficients for our second order differential equation are not constant, right? So they're functions of the independent variable x. Okay, so you have a, b, and c are are numbers. We're going to assume x is positive, and we're going to try finding solutions to this in this kind of, well, not naive, but let's say assuming that a solution would look like that. X to some power r. So the question is, what value of r, or values of r, would make this a solution? Okay, so since we assumed the form of a solution to this homogeneous equation, to figure out what r makes this work as a solution, well, we would have to differentiate once, twice. And then we would plug that into our differential equation. You get a times x squared times y double prime plus b times x times y prime plus c times y. Simplifying, x to the power r is a common factor. Since x is positive, x cannot be 0, so x to the r cannot be 0, meaning that this polynomial in r has to be 0. I'm just going to distribute and combine like terms, and then we see we have a quadratic in r. And let's say we just use a quadratic formula to solve for r. So these values of r formulaically would give you a solution to the Euler differential equation. Now we know that since we get a quadratic equation, there are some possibilities for the roots. The roots could be real. I don't have to say possible. So the cases for the roots. The roots could be real numbers and distinct. So real, distinct roots. The next case is that we have real roots, but they're repeated, right? So r1 equals r2. So you have repeated roots. And finally, it's possible that your roots are complex conjugates. Right? So if your roots for your quadratic are complex, they're going to come in a conjugate pair. Okay. So then, for the three cases, case number 1, the solution to this homogeneous differential equation is a combination of, well, we said that x to the root works, right? And since these are distinct roots in case 1, these x to the r1 and x to the r2 are linearly independent. So we have a fundamental solution set, x to the r1, x to the r2. For the second case, and we will try to explain why this is true when we look at the deeper background machinery that's going on here. But right now we just want to get formulas, apply them to some concrete examples, and then we'll go back and see why all this stuff works. So for the repeated root case, your first solution is just x to the r. Just say the repeated root is called r. In the second case, it would be like x to the r, but you have to multiply it by something, and to get it to be linearly independent from the first function in the fundamental solution set. So it turns out the thing you're going to multiply by is natural log of x, right? Now remember, x is positive, so this is completely defined. And then x to the r. So the third case, where the roots are complex conjugates, you're going to have that. So here, okay, so for case number 2, the fundamental solution set is just x to the r and then log of x times x to the r. Right, so log of x, right, that's multiplying x to the r. The third case, where the roots are complex conjugates, your solution is going to be a combination of x to the alpha, which is the real part of your root, times, let's say, sine of log x, beta log x. So that looks really weird and mysterious, but we'll again see why this is the form. So beta is the imaginary part. And of course, the cousin to sine, right, is cosine. So your fundamental solution set is x to the real part of your complex conjugate, your complex root, and then sine beta log x. And then the second linearly independent solution, use cosine instead. That's your fundamental solution set. Okay, now we're going to go through some examples of these three cases. If we ever forget the polynomial that characterizes this Euler differential equation, you can always quickly rederive it by assuming the solution in the form of x to the r, differentiating a couple times, and then substituting into the differential equation. That will rederive the characteristic polynomial for our Euler equation. So x squared times y double prime minus 3x times y prime minus 5 times y. You can factor out x to the r, and we know that x to the r is not 0 since x is positive. Therefore, this polynomial has to be 0. And here I can use quadratic formula, but we also see that obviously factorable. So here we have two roots. First root is 5, the second root is -1. So we have the real distinct roots case. So our solution to the Euler equation, general solution, is a combination of x to the r1 and x to the r2. So next we're going to look at an example of the second case, a repeated root. We assume a solution of that form, differentiate twice, and substitute. Since x is positive, this polynomial has to be 0. Our quadratic is factorable, it's a perfect square. So we see that r equals 3 is the only root with multiplicity 2. It's a repeated root. So according to the formula, which we haven't shown why that works, the solution, the general solution to our Euler equation is a times x to the root 3, then b, and then we're going to get x to the cubed, right? But we also want to make the second solution independent of the first one, so we're going to multiply by natural log of x. Okay, so we're continuing with our cases, example of cases. The last case, of course, is complex roots. Assume the form of the solution, differentiate, and substitute y and its derivatives into the Euler differential equation. We factor out x to the r, which cannot be 0 since x is positive, foreseeing this polynomial to be 0. We solve for r in our characteristic polynomial for the Euler equation. I'll use quadratic formula. So we see that our roots are conjugate pair. It is a conjugate pair. The real part is 2, the imaginary part is 3, or minus 3. So according to the formula for the third case, your solution is a combination of x to the real part, so that's x squared, sine of imaginary parts of 3, log x, and x squared cosine 3 log x. I'll be right back. Now we actually want to derive all these formulas. Well, the first case is just justifies itself because it works. But we want to maybe justify the other two cases. And to do that, we have to see what's really going on. And since x is positive, we're actually going to assume that x is equal to e to the t, right? The exponential function is always positive, so this is valid substitution. And it's a substitution of the independent variable. Note that this also means that natural log of x is t. To be clear, when we look at this Euler differential equation, the independent variable here is x. So these derivatives, y prime, y double prime, are derivatives with respect to x. So I'm just going to make that explicit. Now we're going to have to do a substitution where we see that any place we see x, we can replace e to the t. But we also need to replace the derivative of y with respect to x in terms of the new independent variable t. So this is just an application of chain rule. We're going to have the derivative of y with respect to the new variable t, and then derivative of t with respect to x. Well, since we know that t is log x, then the derivative of t with respect to x is just 1 over x. But of course, we want no x's, right? We want to get rid of the old independent variable and bring in the new independent variable t. But 1 over x, since x is e to the t, it's just 1 over e to the t, which we can write as the derivative of y with respect to t times e to the minus t. So there we go. We have put that in our back pocket. Well, we're going to use, yeah. So we have one formula here. But we also need the second order derivative replaced. So second order derivative of y with respect to x. So this is just the first order derivative of the first order derivative of y. Notice that, well, we can use chain rule, no? So chain rule again. We're going to first differentiate that with respect to t, okay, and then multiply by the derivative of t with respect to x, chain rule. So dy dx, we already computed over here. And dt dx, we already know is 1 over x, which is nothing but e to the minus t. So now, both of these are considered to be functions of t. So we're just going to use product rule there. So now we know that, so we're going to complete our substitution where x is replaced with e to the t. dy dx is replaced with the derivative of y with respect to t times e to the minus t. And the second derivative of y with respect to x is replaced with. All right, so let's see. Looking at the original, you get a times x squared, so that becomes e to the 2t. The second order derivative with respect to x is replaced with its equivalent. So the next term is b times x. X is replaced with e to the t. dy dx is replaced with its equivalent. And then we have plus c times y, where y is now considered a function of t. And of course, the beautiful thing is that the exponentials go out. Multiplying these two gives you e to the 0. Multiplying these two gives you e to the 0. We see that these exponentials when multiplied give you e to the 0. Also, the exponentials in green, when multiplied, also give you e to the 0 or 1. And then we group by the order of the derivative. So the transformation of the independent variable, where x is equal to e to the t, turned the Euler differential equation, which has non-constant coefficients, into a differential equation with constant coefficients. And we know how to deal with this. For differential equation with constant coefficients, we assume that a solution as a function of t looks like e to the rt. After we differentiate a couple times and plug that into our differential equation, we get a characteristic polynomial. So we get a r squared plus b minus a r plus c 0. Next, we solve for the roots. So I used quadratic formula, and we know that depending on the nature of the roots of this characteristic polynomial, we know our fundamental solution set. So let's go through the cases. First case is that the two roots are two real numbers which are distinct. So the solution to this differential equation with constant coefficients, here we have y as a function of the independent variable t, e to the r1 t, and the second function in our fundamental solution set is e to the r2 times t. These are linearly independent because the roots are distinct. Now we just use properties now to see what the fundamental solution set is in terms of the original independent variable x, we just use properties of exponents. Remember that x is e to the t, so that's x to the r1. Likewise here, it's x to the r2. So the fundamental solution set in terms of the independent variable x to the original equation is so. The second case is where the roots are real numbers, but repeated roots, right? So multiplicity 2. Let's call that root r. So the fundamental solution set in terms of the independent variable t is e to the rt, and the other function in our fundamental solution set is e to the rt, but multiplied by t to guarantee independence. Using properties of exponents, we see that in terms of x, one function in the fundamental solution set is just x to the r. Now, for the second function in terms of x in our fundamental solution set, you notice that if x is e to the t, then natural log of x is t. So here we have t times e to the t to the power r, while t is log x, and e to the t to the r is just x to the r. So that mysterious log x, right, when you have repeated roots in an Euler equation, is explained thus. The third case is where we have that our roots are a conjugate pair in terms of the variable, independent variable t. You know that our fundamental solution set is an exponential using the real part of our complex root, and a sine cosine, which uses the imaginary part of our complex roots. If we want to write the fundamental solution set as a function of x, then we use our change of variable, so e to the t is x, and t is log of x. So that explains this fundamental solution set for the Euler equation in the case of complex roots. So now we can return to more examples of the three cases for Euler's equation. But just to summarize, we have a Euler differential equation. It's the first example of a second order differential equation where you don't have constant coefficients. We derive the formula for the characteristic polynomial, either by assuming that we have a solution in the form of x to some power r, or more rigorously doing a change of independent variable where x is e to the t. And this turned our equation, which didn't have constant coefficients, into one which does have constant coefficients. And we know how to deal with this case. And this allowed us to derive the three cases, or a fundamental solution case, fundamental solution set, in terms of y as a function of x. So let's do an example. I'll just use my formula for the characteristic polynomial for an Euler equation. So a is 1. So a is 1. B is negative 3. So b minus a is negative 3 minus 1, so negative 4. And c is 4. So we see that this is factorable. And we have case 2. We have a real root with it's repeated, so multiplicity 2. So according to the fundamental solution set in terms of variable x, it's just x to the r. And the other function is log x, then times x to the r. Let's do another example. We'll use the formula for the characteristic polynomial. So a is 1, b is 3, so b minus a becomes 3 minus 1, c is 10. I'll go ahead and use the quadratic formula since I can't factor out this more easily. So So we see that the roots are complex conjugates. The real part is -1, the imaginary part is 3 or -3. So this is a third case. So we know the fundamental solution set is a function of x. We have x to the alpha times sine beta times log x. The second independent function is going to be x to the alpha times cosine beta log x. Let's do a final example. Using the formula for the characteristic polynomial, b is 5, a is 1, so 5 minus 1. This looks like it might factor. So we have case number 1 where we have real distinct roots. So the fundamental solution set is x to the first root, then we have x to the other root. See you next time.